So we were in the middle of covering reactions, and one of the products of a reaction that we're going to be looking at is called an Osa Zone. I really only cover it because you see it everywhere in all the texts. Historically, they were used to identify different sugars. It was helped to identify the different structures of sugars. And so I'm going to explain to you what it is. We'll start with the drawing of glucose. So glucose, if you remember, looks like this. This is sort of that reduced format that I use. But at the top, instead of just leaving it blank, I'm going to draw a C and then double bond O and then H. So that's glucose. Again, remembering that there's oxygens at every one of these carbons. And on the other side of these Fischer diagrams, we have hydrogen. So I'm going to leave those off. There's just more work than you need. And what they use in this reaction is phenol hydrazine. So phenol hydrazine looks like this. And it forms an imine type product, which is in this case called an Osa Zone. And it's two equivalents of this. So it's whatever you have twice as many moles of the phenol hydrazine. And what you'll end up with is a structure that's glucose at the bottom. So I'm going to just draw this like this again. But at each one of these carbons, you have a nitrogen double bonded to a nitrogen and then a phenyl group, NH, and then I'm just going to go like this, pH, like that. And then again here, NH, pH. And what's interesting about these compounds is many of the sugars react to form Osa zones, and their crystal structures are very different. But some give the same crystal structure. So if you do the same reaction with fructose, glucose, and mannose, you'll notice that you get, I'll zoom in, and I stole this, I should have put a citation in, I stole this from the internet. These are the crystals that you get from glucose, fructose, and mannose. They call these broomstick-like crystals. You'll notice it has like a handle, and then it's got the broomstick part sticking out like that. They make these characteristic crystals, and then other sugars will give different shapes. The reason that glucose, fructose, and mannose give the same structures is because this part in each of their structures is the same. And so one of the ways that this information was used in identifying the structure of glucose and mannose, both being the aldose sugars, was that the Osa zones were the same, so they knew parts of their structure were the same. And we'll get to that when we talk about Fischer's proof. So glucose, fructose, and mannose give the same crystal structures because C, and remember this is a 1, 2, 3, 4, 5, 6, C3 through 5, have the same stereochemistry. And so that information got used in helping to determine what the structures were. Before I go on to the cyanohydrin reduction, I want to really quickly talk about the cyanohydrin mechanism. Cyanohydrins are more important in aldehydes because aldehydes generally are more reactive. And so I'm going to start with an aldehyde like this, right? And then we do Cn minus in the presence of HCN. And it doesn't really matter how you get this combination, but it's a trace amount of Cn minus. So in essence, you have to have a pH that's close to its pKa, which is close to 9. And when you're close to that, you have a small amount of that cyanide ion present, and predominantly HCN, and your product will be this. And in the context of what we're doing right now, the thing that's important to recognize about this carbon is chiral. It can be chiral anyways. And it can have a pair of enantiomers. So let's do a little bit on the mechanism. We'll talk about that. And then we'll talk about the reduction reaction. So The mechanism is pretty straightforward. You have a small amount of Cn minus that's present, and this is the nucleophile. So it's a nucleophilic addition reaction. And oops, sorry, you get this. Now, something to recognize in this reaction, and this is where the stereochemistry comes in, is the cyanide could either approach from one side, the front, for example, or the back side. And when it does that, it produces both of the enantiomers. And because the carbonyl is flat, you get a racemic mixture that comes out as a product. So then the next step is HCN. And then I have my electrons here. Picks up. And so out of this you get your product, which is this. And then also you get Cn minus. And the cyanide then, it turns out, is catalytic in this reaction. So you make a small amount of it. You have a small amount of it present in solution by putting sodium cyanide, for example, in equilibrium with HCN, or actually sodium cyanide. And a lot of times what people do is they'll add hydrochloric acid to it. You do have to be careful because HCN is the same gas they use like in gas chambers, so it's pretty deadly, and it tends to off-gas unless you keep it and force it to stay in solution by keeping it basic. So it's one of these experiments or these reactions that doesn't get used much anymore just because they're kind of dangerous. Anyways, this is how you get to the product. Okay, so the next thing I want to talk about is the reduction part. And that brings us actually to this Chirality-Fischer synthesis. So let me go over that real quickly, and I'll show you how the reduction takes place in there. So when I do the Chirality-Fischer synthesis, this is a synthesis reaction for making or extending, let's call it that, extending sugars. For example, C5 to C6, that would be an example of a type of an extension that you would be doing. So to do this one, then I'm going to start with arabinose. And arabinose is the sugar that glucose gets made out of. So it looks like this. But then at the top, that's it. So that's my C5. Let me put this down here. This is arabinose. And it's D-arabinose, right? Because of the right-hand position of the lowest chiral carbon. And again, I'm going to draw it out like this. And the first step is actually the cyanohydrin reaction. This, by the way, the cyanohydrin reduction, there's a hyphen in there. And the reduction part I'm going to show you in this Fischer, Chirality-Fischer synthesis. So to D-arabinose, we use Cn minus. Let me write it like you would maybe see it in a reaction. You would see NaCN, HCN, or you would see NaCN and HCl, and those both result in the same sort of reaction mixture, except for the chloride, but that turns out to be not important. And then what happens is you get this. Let me draw this out. Okay, so what I've done is added a carbon to this, right? And so when I've added the carbon, the way it's been added, this is just bothering me. It's going to be added like this. CN will be at the top, and it'll form a new bond to this carbon here. And then from that structure, hang on, I'll do something real quick. Just want to copy that. Okay, so from that structure, I generate both of the enantiomers. So in one, this group goes like this, and the other side it goes like that. So those are the enantiomers. Now, this will eventually lead to glucose, and this one will eventually lead to mannose. So let's take the glucose side, and we'll look at the reduction reaction. And in the reduction reaction, they do like they do in Lindlar's catalyst. They use the palladium catalyst. Now, this is the new and improved. This was like, this wasn't actually what Fischer did. What Fischer did is he used a mercury, like a sodium mercury amalgam. And again, that's some of that chemistry that doesn't get used. This is supposedly more efficient. On the other hand, none of these are that efficient. So, but the reduction gives you this. So what you've done is you've created the imine out of it, like that. And then the last step is to hydrolyze that with hydrochloric acid and water. Or aqueous acid solution. It doesn't really have to be hydrochloric acid, but aqueous acid solution. And so you'll end up getting this. So the reagents are H2 and then palladium. And it's a poison catalyst. It's on barium sulfate. And then, if I remember right, one of the catalyst poisons they used might have been quinolone. I can't remember. That may be Lindlar's catalyst, but it's a poison catalyst. And then this is just H2H3O plus. Really, it's acid and water. So H2O plus H plus of some sort, and that'll do the hydrolysis, similar to what we did in the enamine reaction at the end. Okay, so that's how we can extend sugar chains and make them longer to see what sugars they produce. And oftentimes, if my understanding of the what I've read in the past is correct, it's actually separated at this point, and then it's hydrolyzed. It's reduced and hydrolyzed after that. So, anyways. Now, another important reaction in studying sugars is called the rough degradation, and there's a couple of these kinds of reactions that are out there, but rough is the one that usually people talk about in sort of the general organic chemistry class. And that reaction is to take a sugar, an aldose usually, right? That's what we're working with right now, and shorten the chain. So taking, for example, a C6 and then producing a C5 sugar out of it. And so if you can take two sugars and do rough degradation on them and then produce the same, let's say, aldopentose, then you'll know that those two structures are related, and they're what we would call, again, C2 epimers. I mean, they would be differing in their stereochemistry at C2. So let's do the reaction. Let's start with, again, with glucose. That's an easy one to remember. Like that. So the first step in the rough degradation is actually that oxidation reaction with bromine. And then you end up with the gluconic acid. And then it's followed by decarboxylation. And I don't know the mechanism actually for this reaction. H2O2, and then it's iron sulfate. Iron 3 sulfate. But what you get then is you get this guy. Oh, sorry. That's not what you get. One less carbon. plus CO2. So the formation of the carboxylic acid, that's where that's ending up. That is used to do the decarboxylation reaction. So you remove a carbon in the process, and this mechanism here is like a 2-electron reaction where the electrons are transferred apparently in different steps. So you do 1 electron at a time, form a radical. So like I said, I don't really know that mechanism. So now we're in the point with reactions and stuff where we can talk a little bit about how Fischer determined the structure of glucose and subsequently led him to the structures of all the aldose sugars. And it's considered to be one of the great accomplishments in science over the years. So to put it kind of in perspective, it was 1862 that the idea of carbon being tetrahedral came up. And actually it was Kekulé who started it when he was looking at the structure of benzene and structures of molecules. Some of the stuff that, let me put this down, that wasn't certain, in fact, at this point, it was a constant debate, is whether or not atoms even existed. Even though atomic theory was early 1800s, there was still a lot of discussion on whether or not atoms existed and whether or not we just had a theory that allowed us to explain structures and that there weren't really atoms in substances and there was something else yet that wasn't understood. So, I mean, there was a lot of unknown at that point, a lot of uncertainty. Put it in a better perspective, Fischer's proof was around 1888. And so the light bulb was 1879. So that's when Edison invented the light bulb. So you have to think about the kind of stuff that Fischer had his hands on. Well, Pasteur had discovered chirality in crystal structures, and the idea of chirality was considered to be understood, or that chirality was possible. Again, starting with Kekulé, was thought of being a possibility, but really it wasn't until 1848 that somebody came up with the idea, and it stuck. But again, these guys are battling with the idea that, gosh, maybe atoms don't exist. And there was a lot of discussion going on about that kind of stuff. So anyways, Fischer had melting points, so he could do melting points. That's how he identified lots of structures. He had the Osa zones that I mentioned earlier. He also had access to the ability to study optical rotation of solutions, or optical rotation. The first polarized glass wasn't invented till about 1812, and the way they made polarized filters back then is they would just press 2 sheets of glass together. I don't know what they put in the inside, but it may have just been the open airspace, and they could create polarization that way. And then he asked chemical reactions. So Osa zones falls in that category, but there are a lot of chemical reactions. And, you know, the Chirality-Fischer reaction, rough degradation, and polarimetry were really the things that he had access to that were probably some of the more significant thing. So he knew glucose had 4 chiral centers in it. So he knew it was an aldohexose. He knew it had 6 carbons in it, and he knew that it had 4 chiral centers. Let me draw this out. All right. So he knew 4 chiral centers because if it's an aldehyde, and you have aldehyde at the top and a CH2OH at the bottom, there'll be 4 centers which are asymmetric. in the middle. So that would give you your aldohexose. If it was aldoketose, he would have known that it had 3 centers. And so the important part about 4 chiral centers is that means there's a total of 16 isomers. Right? So pairs of enantiomers, right, 2 at a time, but 8 sets of diastereomers at that rate. So another issue that came up was, what's the configuration of glyceraldehyde? So glyceraldehyde, he knew from rough degradation, for example, could either be this, and let me draw the whole thing out. It's just so small. I'm just going to go ahead and do it. Or it could be this. And this is L, or D, sorry, and this is L. And he just assumed that glucose, the glucose he could get his hands on, the D-glucose, was based on this as glyceraldehyde. So he knew the configuration of the bottom carbon, or the second to the last carbon in glucose, C5. Or he assumed. It wasn't actually until the 1950s that they determined the absolute configuration of glucose at C5, and it turned out that Fischer's guess was right. Had he been wrong, there would have been about 70-ish years of data where they would have had to have gone back and shown in each one, put a little asterisk like, well, this is actually supposed to be the mirror image because, right? Because they would have gone back and fixed all the previous chemistry and biochemistry. So what I'm going to do is, I have them actually drawn already, draw the structures on the screen for the aldohexoses of the D configuration that Fischer knew, one of which could be glucose. And then we'll talk about Fischer's proof of glucose at that point. So here are the structures, and I drew them in pairs because Fischer knew that if you made the Osa zones of these, that they gave the same crystals. So he knew that they were paired up. You could also get that information from doing rough degradation and showing that you end up with the same structure from different sugars. But anyways, he knew that there were pairs of them. And so then the first thing he did was he took glucose and he oxidized it. So glucose to glycolic acid. Remember, he doesn't know the structure, right? So he's just going by names. And that's a nitric acid oxidation that we talked about before. And then he looked at glycolic acid, and he noted that it was optically active. So now you can look at a couple of these structures. For example, looking at structure number 1. Remember, and this is one of the reasons why I actually like drawing these structures this way. I'm going to copy it. Now this is in glucose, and you probably know that already. But if you take this and you oxidize the ends to an alderic acid, so both ends are oxidized, it looks like this. And so it has plane asymmetry in it. Now I'll draw it as dashes like this. And so this compound's actually meso. So right away, Fischer can eliminate this structure as the structure of glucose. He can also, taking a look at structure number 7, he can make the alderic acid from it. Sorry, I'm just looking at something else like this. And this is also meso, right? So here's the deal, and this is one of those intuition things. Since structure 1 and structure 7 are symmetric, right, in their alderic acids, you can eliminate 1 and 7. But at the same time, because 1 and 2 give the same Osa zone, you can eliminate 2 and 8. So automatically, by looking at optical activity, he's eliminated 4 of the structures and only left himself with 3, 4, 5, and 6. Oh, so here's another thing that he did. So he eliminated, again, this process of looking at the alderic acids eliminates 1 and 2, and 7 and 8 are eliminated. So that means glucose is 3 or 4 or 5 or 6. He doesn't know which one yet, right? So the next thing that he does is he does a rough degradation on it. So when you do the rough degradation of glucose, I'm going to call it RD. Remember, the reagents are listed above, but rough degradation, you get a Ribonucleic. Again, not knowing the structure of glucose, really he's just working with the names. And then he does the same trick. He goes like this. HNO3. And the result is it's optically active. Okay, so think about what that means. He knows that glucose is either 3, 4, or 5, and 6. So I'm going to copy those down so we can look at those. I'll just pause it while I do this. So there are the structures of 3, 4, 5, and 6. Now think about what he did. He did a rough degradation. And so what you end up with for 3 and 4 is you end up with this. And then for 5 and 6, you end up with this. So I think it's obvious. If the product had been optically inactive, then it would have been this structure. This structure, if you convert it into its alderic acid again, let me move that down. It's a little too close. I can't get my little arrow in there. All right. This is HNO3 and H. Oops, I shrunk it. HNO3 like this. All right. This compound on the right is meso. So if that had been the result, then 5 and 6, one of those two would have been glucose. But instead, because the product was optically inactive, glucose was either 3 or 4. So you notice how he does a reaction, checks the stereochemistry, and because it's either optically active or inactive, he's able to eliminate compounds that way. Again, he eliminates 5 and 6 directly by looking at its aldotetrose. Okay, so now the question is 3 or 4, right? Which one is it? Is this glucose or is this glucose? And Fischer had determined or discovered a set of reactions, a sequence of reactions that he used. And remember, this is CHO and CH2OH. This is CHO and this is CH2OH. he figured out a way to interchange the aldehyde group with the C6 alcohol group. So he's able to switch the functional groups of these molecules. So, for example, if you take glucose and you interchange, this is CHO down here, and this is CH2OH, you can rewriting this 180 degrees, right? This is one of the things you can do with the Fischer diagram. That would give us CHO at the top and CH2OH at the bottom, and then the structure would look like this. So this structure is in fact L-gulose. Now, what happens if you do the other compound? Again, you do a set of reactions to exchange. Sorry, pause here. So what if you do the exchange on the lower compound, right? So again, the series of reactions, I don't know why, but it's not usually mentioned, is this. Gives you this product. So the bottom you have CHO, bottom you have CH2OH, and then again we've just exchanged the functional groups at the top and the bottom. Now we're going to flip this 180 degrees. What do you notice about that structure when you flip it 180 degrees? Right? And Fischer used this reasoning as well. All you get is this. And these two compounds are the same. So in fact, the way Fischer determined the structure of glucose was to show, in fact, that when you do the interchange of functional groups, you end up with a different compound instead of the same one. And so that told him that glucose's structure must be this one, based on the top molecule, CHO at the top, and then CH2OH. Now, so this is D-glucose. And then from this kind of analysis, he automatically knows which one is mannose, and he can do the assignments of structures of all the aldohexoses. So oftentimes students have the question, so how are you going to ask this on a test? And typically what I do is I give a set of data and ask you to, from the data given, determine what the structure of a particular sugar is. And it's not necessarily going to follow the results that Fischer got. So you can't just say, oh, it's this structure. Glucose looks like this, or mannose looks like this, or arabinose looks like this. You'll have to do it based on the information that I gave you. It'll be a sort of a what-if scenario. What if Fischer had done this and gotten this as the result? So the next thing to talk about is the cyclic structures of sugars. And there's a different kind of drawing style, and you see this a lot in biochemistry and biology, and they're called Haworth projections of sugars. Okay. And if I draw one for you, you'll probably immediately recognize this structure. If you've had any biology or done any reading, you will have seen a structure that has this kind of shape. So it's not a chair or a boat. It's just drawn as a hexagonal ring, and we put an oxygen in the corner. And then there's branches that go like this. Okay, and then very quickly, I just want to make a couple of notes on this. These ones where I do the red, right? This is above the carbon in the ring. And the triangles I'll do in blue, these are below the carbon in the ring. like this, okay? So it's not chair or boat, and it's not axial equatorial. We're just sort of flattening it out. But I want to make sure you understand when the line is above the ring, it's above the carbon in a ring. And if for example, here and here and here and here, these are all above the ring in that way. So this is called Haworth projections, and they're used a lot to depict the structures of glucose. So let me show you how you get those and the other aldoses. Let me show you how you get that. Okay, so what I'm going to do is draw glucose again. And then I'll draw CH2OH at the bottom, and then CHO at the top, and then I'm actually going to include the OHs here, because it gets a little confusing if you don't have those, or at least the O's. And this is what happens. Remember, you can take an alcohol and react it with an aldehyde, like this, and you can form a hemiacetal. I'll do OR up here and then H down here. And you know, there's a couple of steps in this reaction that give us that, but that's a hemiacetal. And when sugars cyclize, what they're doing initially, at least, is they're forming hemiacetals. And when they bond together to form polysaccharides, then they're forming acetal bonds. So hemiacetal, let me finish what I'm doing here. And there's a couple of ways that this can happen. And in glucose, the most common way is for this pair to attach to this pair, like this. So right now we're going to call that 1, 2, 3, 4, 5. And then oxygen is 6, so this is the 6. That's the oxygen in the ring, okay? So let me redraw the structure of glucose when it's in this Haworth form. So I just generally start with the skeleton like this, and then I'll go CH2OH. Now, what is the CH2OH, right? So let me do this real quick. I'll highlight it, actually. This is actually this group down here. The oxygen in the ring, like I said, is oxygen number 6. That's actually this guy here. Now, the carbonyl carbon number 1, based on the idea that this is number 6 here, this is 5, and I'm going to draw on the inside 4, 3, 2. So again, this is carbon number 1. That's the carbon that was originally the aldehyde. So when it does this reaction, when the oxygen comes in and attacks, that's this oxygen here comes in and attacks, and it forms this hemiacetal, then there's an OH that extends from that. That's this guy. This O is this O here. So that means on carbon number 1, I need to have an OH group. So that OH group can be drawn, for example, like this. Or it could be drawn the other way. It could be drawn going in the downward direction. So let me draw that real quick. And then I'm just going to pause the video while I do some of these drawings because they take a long time. So that's what it looks like. So the question is, where are all the other OH groups? Because they're going to have a definite stereochemistry on this structure. And then I'll talk about why the red hydroxy group, the alcohol functional group, one time it's pointing up and one time it's pointing down, right? So on carbon number 2, we have a group, well, I'll do it in red, that's fine. I have an OH that goes down. And carbon number 3, I have an OH that goes up. And carbon number 4, I have an OH that goes down. And again, remember, on carbon number 5, the OH that was on carbon number 5 is now in the ring in yellow. So those configurations, 2, 3, and 4, don't change in these Haworth projections. These are always the same if it's glucose. What does change is the position of the OH group that I've drawn here. And if it's going in the upward direction, then it's called beta. And if it's going in the downward direction, it's called alpha. And I always just tell people, just remember, write alpha down. And if you put an A in there, that equals rad, right? So it's rad. That helps you remember the association with the direction and whether or not it's going up or down. So here's the thing. What does the right stand for? Right? The right stands for here. So also the alpha. Okay. Back up for a second. This can be used for two different things. One is to name whether or not it's an alpha or a beta, but also if it's to the right on the chain, carbons 2, 3, and 4, it's also down in the Haworth projection. So since carbon number 3 is to the left, it's upward. Now, kind of a simple and funny way to remember this. Let me see if I can do this. I'll try it. Is if I take this structure and I turn it on its side like this, right, you'll notice carbons 2, 3, and 4 are in the same configuration as they were on the parent chain if you just took this thing and you tipped it over on its side just like this. Okay, so the other way to remember right is down is just simply looking at the structure and think to yourself, well, if it fell to the right, then anything to the right would be down and anything to the left would be up. So these are the glucopyranoses. Pyranose stands for 6-membered ring. So there's actually a fructopyranose, and a 5-membered ring is called a furanose. So this lower structure is alpha glucopyranose, and the structure up here, this is beta glucopyranose. Now, just a little side note, you notice how on both of these structures, carbon number 6 is in the upward direction. If you're doing, these are for the D glucopyranoses. You could also shove a D in there if you wanted to. If you're doing the L sugars, then usually this is drawn in the downward direction. Again, this other little stem, which I didn't label down here, is just the hydrogen that's attached. Well, actually, it's it's the hydrogen that's attached to that carbon. So it's the one that I've not drawn over here. So as I mentioned, a pyranose is a 6-membered ring, and a furanose is a 5-membered ring. And I thought I'd show you how you draw that for glucose. So again, you start by drawing glucose. That's the easiest way for me to remember how to do it. These are the OHs for the chiral centers in glucose, and this is C double bond O like that. And then you have CH2OH at the bottom. So to make a 5-membered ring, again, you have to attack the aldehyde group. So we'll still call this 1. This will be 2, 3, 4, and then the oxygen is the 5th member of the ring. And so what will happen is you'll redraw a 5-membered ring. Now typically the furanose is drawn with the oxygen to the top, like this. And then carbon number 1 is here. And so 1, 2, 3, 4. And then carbons number 5 and 6 project upwards. And so for glucose, it's like this. And this is CH2OH. So it has this chiral center here that I just drew, as well as 3 on the ring. So again, the anomeric carbon is carbon number 1. This, if you remember right, that carbon was originally this guy here. And so that carbonyl group becomes an alcohol, and it can point either in the upward or downward direction. So if it's going down like this, let's do like that. Ooh, it's a fat pen. Let me get this other red pen. It's going down like this. This is the alpha form. So this would be alpha D, because it comes from D-glucose, and then glucofuranose. The same trick applies. If you know where carbons 2 and 3 are, then for carbons 2 and 3, you can go down like this. All right, that. And then, let's see, and up like that. Now, carbon number 4 has a hydrogen sticking out like this. And that, if you remember, there's a hydrogen here, and then this carbon number, oxygen is here. This is the 5th member of the ring. It attacks the carbonyl, which is in green, and then that leaves the hydrogen. That's the only thing that wasn't left drawn on there. So that's what alpha D glucofuranose looks like. Another real common furanose that you see is fructose. So what I'll do next, because I don't think I left a slot on here, I'm going to draw fructofuranose. So this is going to be alpha D fructofuranose. And in order to draw that, what you need to do is first draw fructose. So if you go back to the ketose sugars, you'll see that it's, remember, it's the same as glucose, like this. But it's C2, that's the carbonyl, like that. And then there's a CH2OH, like this. And on the bottom you have CH2OH. So what you want to happen is you want to have this carbon attacked by one of the oxygens and leave you with a 5-member ring. So start counting from that carbon. I'll do it in red, just make it stick out. 1, 2, 3, 4. And then so the 5th atom was the oxygen. That's this guy here. So now what you can do is draw a 5-membered ring. And then at carbon number 1, this is, sorry, I'm going to draw 1 again. Carbon number 1, this is your anomeric carbon. And so if I say it's alpha, it's going down. So it'll be going down like this. And again, 2 and 3, sorry. This is 2 and 3. You can still do that same trick. So at carbon number 2, the OH is going in the upward direction. I think it's going in the upward direction. Yeah, it's going in the upward direction. And 3 is like this. And let's see, what else do I have here? Oh yeah, and then on carbon number 4, I have this. Now on carbon number 1, I also need to have a CH2OH, and that'll opposite of the OH group. So that guy is here. So let me color code these things a little bit for you. So this group is, let's see, this one, and then this one is this guy here. And the oxygen that was the carbonyl, I'll go ahead and put that in this color, is actually, that was the carbonyl oxygen right there. Okay, so on carbon number 1, you're going to have a CH2OH as well as the OH from the original carbonyl oxygen. So I wanted to show you one other thing, and this is an important, because glucose is such an important monosaccharide. I wanted to show you a little bit more of the details of its structure when we draw it this way. To start with, if we look at the alpha form is going to be this. So this alpha means it's down, right? Like this. And then if you remember, it's down and up, and then down. And then on here I have CH2OH. So this is alpha D glucopyranose. Oops, I didn't leave myself enough room there. So that's alpha D glucopyranose. If you were to draw that in a chair configuration, the oxygen would be at the corner. That's right here. And so in the most stable conformer, and that's really what we're interested in, we want the CH2OH to be in the equatorial position. And if you do that, what that means is if this group is put in the equatorial position, if you remember what that does, that forces all the other groups like that are opposite, like this, the next adjacent group, that is equatorial. And then this is equatorial. And then we have equatorial here. And then we have, oh, I didn't leave myself quite enough room. Let's try this again. I have an axial like this, because if two are adjacent to each other, one can be equatorial and one can be axial. So what that means is if I look at beta D glucopyranose, that's going to have this configuration. Equatorial here, and then everywhere else is equatorial. So when we're looking at the monosaccharides in aqueous solutions, we can actually just look at all equatorial, right? And predict that that's the more stable of the two conformers, and so, or actually isomers of each other. And so this actually represents about, when this is in solution, about 64% of the glucose, and the other side represents about 36%. And most of the time, almost all of the sugar, all the monosaccharides are in their cyclic forms when they're in aqueous solutions. Another aspect that I wanted to show you is how you can quickly draw the other monosaccharides, the hexoses, in their Haworth form. So let me pull a couple of structures out for you. So here are the structures for glucose and talose, and so I want to show you how knowing the structure of glucose allows you to figure out what the structure of talose is relatively quickly. So again, to draw glucose, the way I try to remember it anyways, is I try to remember the beta form. You can start with this one. This is this group. This is CH2 on top. And then all the other ones are opposite, like this. And the beta form goes up. So that would be the more stable of the glucose anomers is what we call them. So now, remember, this is carbon 1, 2, 3, 4, 5, and 6. So you have to remember that. But to draw the structure for talose, all you have to do is recognize that they're actually only different, let's see, here and here. So those are C2 and C4. So what you do when you draw talose, if you can remember glucose, rather than going through the whole drawing it on its side and stuff, you can just draw the Haworth, just like as if you were, drawing glucose. The CH2OH goes on top, and then carbons 2 and 4 are opposite. So it would look like that. And then whether or not it's alpha or beta will determine whether or not this is going up or down. And a lot of times the way we designate either possibilities, we use that squiggly line and attach it to the OH. So that generally represents both the alpha and the beta. And then by swapping, by seeing that these were the groups that were swapped on the ring, or on the chain, this group here, we're able to draw the pyranose version of talose relatively easy. So that would be alpha and beta D talopyranose is how you would name it. Yeah, so when I made these slides, I wasn't sure if I would have room to fit all this stuff in up here. So I have a little extra space here. So let's just really quickly review acetals and hemiacetals. Okay, so if you have an aldehyde and you have a catalytic amount of acid, and let's just say ROH, what you end up doing is protonating the alcohol, and then we do a nucleophilic addition reaction, and you'll end up with this. And this is the hemiacetal. If you continue to heat this with acid and an excess of the alcohol, what you'll end up getting is this. And this is known as the acetal. So the acetal is formed from the hemiacetal. And so when we're looking at sugars, and they're forming bonds with each other to make, let's say, disaccharides, you have to think about what a hemiacetal and an acetal looks like. So let's take a look at glucose really quick. So glucose forms this kind of structure, and let's say it's pyranose. I'm not going to draw all the other OH group, but the pyranoses in general could have, for example, an OH group like this. So that would be the beta. If it was going down, it would be the alpha. On the other side, we have the hydrogen, and I don't usually draw that in there. So notice what you have here. You have an alcohol on one side, right? The alcohol on one side, or the alcohol functional group, and then you have an OR group on the other side. So this is my OR group like this, and the hydrogen. So in fact, when we're looking at the cyclic forms of the sugars, of the monosaccharides, those are all hemiacetals. Now, when you take two sugars and you link them together, so let's say I take, so rather than drawing it all, sorry, I paused the video recording, and I just copied it. And so, like in glucose, that carbon number, 1, 2, 3, 4, carbon number 4, the OH goes in the downward direction. So I'm going to draw this. So when the hemiacetal is converted into an acetal, this is when two monosaccharides bond together. This green OH that's here, this leaves as H2O. So in the drawing that I've done now, you'll see that when I link these from 4 to 1, what's going to happen is this green group that's here is going to leave as a water. The direction in which this bond goes is determined by where this OH is, because that one is fixed in the sugar. This OH can be either up or down. So what happens in the linkage is that you're going to have a bond that forms like this. And the way it's drawn is they draw it down and up, and then they draw a second one like this. So this is known as an alpha glycoside. And a glycosidic bond is really that acetal bond that exists between the two sugar residues or monomers. So glycosidic. Is this acetal bond between two sugars. So we have alpha glycosides and we have beta glycosides. In a beta glycoside, it could look like this. Now, if this is to glucose, then this sugar molecule will be up here. Because, again, this bond that I'm circling with the pointer has to be down below this ring. That can't change in the formation of the glycosidic bond. So that's going to be something like this. And so this would be a beta glycosidic bond. So in general, glycosidic bonds are alpha and beta. So for example, if I reacted with ethanol, I could form a glycosidic bond, a glycoside. Let's say this is a OH, like this. And I go ROH as an alcohol. Then what I'll end up with is this. And this could be alpha or beta. So this would be O and then R. That would be the beta glycosidic bond. And you can also have this. I guess you just draw the other line there. These are H's, like that. So this would be beta, and this would be alpha glycosidic bonds. And these two structures are known as anomers of each other. So they're anomeric forms, because we call that carbon, where you could either have it going in the up or the downward position, the anomeric carbon. The other thing I wanted to point out is this would be a glucoside. If this was glucose, that's what they would call it. And if it was a mannose, it would be mannocide, which sounds like you're killing a man, but it'd be MANNO and then SIDE, not CIDE. CIDE is that suffix they use for like poisons and stuff, like herbicide and stuff. Anyways, having said that, there's an important effect that's called the Animerica Effect. And if you look at these two structures, the beta and the alpha glycosides, you might predict that the beta glycoside is the higher percentage than the alpha glycoside, but you would be wrong. And so if you run this with H+, what you actually find is that the major product is the alpha. So the major product is the alpha, even though the alkoxy group that's down here is in the axial position. And sort of to understand this anomeric effect, we have to go all the way back to beta eliminations and understand or sort of relearn the idea of orbital overlap when you do anti-eliminations. So just to review, when we do beta eliminations, the beta hydrogen that's eliminated and the leaving group have to be anti to each other in order for the elimination to take place. So just to review why that is, if you think about, let's say, a simple alkyl halide like this. I have a hydrogen here, that's my beta hydrogen, and then I have a halogen over here, so it doesn't really matter what it is. Let's say it's Br. And then I have a strong base, like, I don't know, it doesn't really matter. Let's do T-butoxide, like this. It's going to attack the hydrogen. Those electrons will dump into a pi bond, and this bromine will leave. So why does it have to be anti? And the answer comes in understanding what the orbitals look like. So what I'm going to do is I'm just going to draw these bonds, okay? And that makes it a little bit easier to think about. So if I'm just drawing those bonds, I have a hydrogen here, sigma bond, and there's carbons in here like this, and another sigma bond, and there's my bromine. And then these are bonded through sp3 hybridized orbitals on the carbons, like that. When the pi bond forms, what happens is the electrons that are in this bond have to have a place to go. And they can't just go into empty space. They have to fit into an orbital one, and the orbital has to be empty and able to accept the electrons. And so while bromine is bonded down here through this bond, right? The bromine, in fact, this sp3 hybridized orbital, there's an anti-bonding orbital that is in exactly the opposite direction. And so there's an anti-bonding orbital on this side as well. So the electrons dump out, oops, in pen, they dump out, oh great, that's okay. Let's do it like that. They dump out from here into this orbital. So what ends up happening is, in the final bond formation, you have a carbon, and then each one of them has an unhybridized p orbital. And then those electrons that got dumped into it came from that yellow bond that's over here from between the carbon and the hydrogen. This orbital, which is unhybridized, came from the yellow orbital. And this orbital, which is unhybridized, came from the green orbital with the bromine. So you have to have this anti-configuration for the best orbital overlap for the reaction to take place. So with that in mind, okay, we can talk about why the Animerica effect makes the alpha form the major product and the beta form the minor product. So this is how the Animerica effect works. What I've done is I've drawn just one side of the Pyranose or Furanose, doesn't really matter, but and it included the glycosidic bond. And what I've also drawn is the lone pairs of electrons on the oxygen. So if you remember, on a ring, in order for beta elimination to occur, the leaving group and the hydrogen need to be axial to each other. So if you'll notice, this is equatorial here. That's the beta form, and this is axial here. So this is actually set up in the form that you would expect if it was a beta elimination taking place. What that actually means is there's a sigma star antibonding orbital here, and these electrons in this orbital contribute to the electron density in this orbital. So this actually has two effects. But I just want to, before I talk about those, the other thing to look at is when it's in the beta form, the antibonding orbital, this is equatorial, so the antibonding orbital that's on this alkoxy bond over here is not lined up with the pair of electrons here, and it's not lined up with the pair of electrons here. So this pair of electrons can't dump electron density into the region between the oxygen and the carbon. So what does this do? Well, if you put electrons in an antibonding orbital, it makes this bond weaker. So, in fact, the bond is weaker in the sigma and the alpha form rather than in the beta form. But the other thing that it does is it makes this bond stronger. So what ends up happening when you have these anomers forming, because the carbon-oxygen bond in the ring is stronger than in the alpha form than in the beta form, it dominates in the equilibrium. And so there were many years where people sort of argued, like, why does this occur? But it turns out it has to do with this electron delocalization into the antibonding orbital. So to finish up this chapter, we start looking at polysaccharides. And so the first set we'll look at are the disaccharides. Maltose is a disaccharide of glucose, and the way it's linked together, and I'm not going to draw all the substituents on the glucose, but I'll just draw the general ring like this. It's connected in this fashion to the glucose molecule that's next to it. Like that. And then this carbon can be either way. Now, this configuration is in the alpha configuration, and we would notate this as an alpha 1,4' glycosidic bridge or bond between the two monosaccharides. So it's an alpha 1,4' 4 prime. The prime is because it's on a different ring. This anomeric carbon can either be in the up or down position, so you have alpha maltose and beta maltose. And again, these are two glucose molecules. And so while the carbon number 1 is alpha in between the two, or could be beta between the two, right? In glucose, this side is what is referred to by this, and this side is part of the structure of glucose, so that can't actually change. Now, a very closely related disaccharide is called and it's actually cellobiose, which is related to cellulose. It's the dimer, it's the disaccharide that builds up to form cellulose. And in that structure, what we have is again, this linkage, and then this is in the beta form. So this is a 1, right, to 4, and then the oxygen is in between, so 1 to 4. 1, 4 prime, beta glycosidic bond. So interestingly, if you look at these two structures, the alpha glucose, the maltose is easier to break this bond because the Animerica Effect stretches that bond out by occupying the antibonding molecular orbital, and the cellobiose, this bond is actually stronger than in maltose. So this is one of the reasons why when we digest foods, it's actually easier, and we don't have the enzymes and stuff like that, but it's easier to hydrolyze maltose than it is to hydrolyze cellulose. And again, this bond can be either in the alpha or beta position, so you have both alpha and beta cellobiose. Sorry. Let me rewrite that. It's not coming out very well on my pen for some reason. Maybe I was trying to write too small. Anyway, so we have alpha and beta forms as well. But the fact that this bond is in the beta position is what makes it cellobiose. And again, this bond here has to be in the downward position because it's glucose. The last disaccharide that's important to know is sucrose. And so sucrose is what we call table sugar. And it's the disaccharide made with glucose and fructose that is our table sugar, right? So let me draw that out for you. So I drew the structure for sucrose for you, and you'll notice it's drawn differently. And if you remember, on glucose, this is the anomeric carbon, and on fructose, this is the anomeric carbon. That's actually the position at which the ring can reopen, and it can become in the open chain form. So if you look at cellobiose, I still have the anomeric carbon here, and I still have an anomeric carbon here. So these can both open up into the aldehyde forms. Now, so it turns out that this distinction makes it so that there is no partially open chain form of sucrose. And that makes a difference in how we test for sugars. And so I'll write one little side note here. We do something called a Tollans test. If you were exposed to the Tollans test when we were finishing out the semester in the fall, and we did the silver mirrored Christmas ornaments, and that's Tollans test. And that's actually a test for open chain sugars, aldehyde sugars primarily. And so when you look at Tollans reagent and it reacts with an aldehyde, and I don't want to be too vague on this, but it will also react with some ketose sugars as well, and I'll talk about that perhaps in a second. But what you end up doing is it's an oxidation method to form a carboxylic acid, so the alderic, the aldonic acid, and at the same time, silver ion becomes silver solid, like that. And that's where we get our silver mirror from. In order for sugars to do this, they have to be able to open up at the anomeric carbon. So taking cell bios, for example, I can reduce that down because it turns out there's an open chain form of cell bios. Oops, sorry. It looks something like this. So on this side it stays closed because it has this glycosidic bond on it, but or the acetal bond. But on this side, it's a hemiacetal, and hemiacetals can open up that bond and revert back to the aldehyde. So remember, there's a CH2OH up here. There'll be an H here, and then a CHO, and this can be oxidized by Tollans reagent and a number of other, actually there's a couple other reagents that are like Tollans reagent that will do that. So Tollans reagent can be used for that, and we call these kinds of sugars that are in equilibrium with their open chain form, we call these reducing sugars, and sucrose is a non-reducing sugar. And the reason it's non-reducing is they're connected together by their anomeric carbons, and it's not easy for them to revert back to their open chain aldehyde or ketone form. I should point out, I guess, since I'm on the topic, if I drew fructose and told you it oxidizes with Tollans reagent, you should initially be a little skeptical, because fructose is this, and then a CH2 on the OH on the bottom, and at the top I have a CH2OH. And the reason you would be skeptical is that's a ketone, but it turns out when you have this alpha hydroxy group on this side, you can go through an equilibrium through what's called an enediol. It was actually in my notes earlier, and I just sort of thought I wouldn't talk about it this time, but so this can form the enediol that looks like this. And it's called an enediol, I guess, for semi-obvious reasons. That it's an enol, but it has two alcohol groups, one on each end, and that this will actually convert over to both mannose and glucose. And then once it's in the mannose glucose form, it can react with Tollans reagent, and then by reacting with Tollans reagent, then you can pull this equilibrium. This is actually an equilibrium in basic solution, so this requires base. And Tollans reagent is in a basic medium. So the base in Tollans reagent allows the enediol to form, and that causes the interconversion of fructose to mannose and glucose, and then you can oxidize it. So now I want to talk about polysaccharides, and when you're going through the slides, don't get confused. There's actually this whole page up here, which was just what was left over of what I thought I couldn't fit in here, but I talked about the notation for the glycosidic bond and the alpha-beta notation. And so we're going to talk a little bit about polysaccharides now. So in a polysaccharide, the polysaccharides you're probably familiar with are starch, and starch actually consists of two polysaccharides in a mixture, basically. So I have starch, and starch is about 20% of a compound known as amylose. Now, because there's so many residues, sugar molecules, monosaccharides connected together, I generally make a simplified notation. I start off by describing it like this. Kind of thinking this is the way modern language actually started at some point. And this is 1 and 4, and it's an alpha, so 1,4 prime, alpha glycosidic bond. So in the glycosidic bond, there should be an oxygen in there. It should be pointing down because it's alpha. Remember, the glucose on this side is pointing down because that's just the structure of glucose. So I start with that, and then I very quickly revert to this. Okay, so that represents the individual residues of amylose. So amylose is linear. It's a 1,4, continuous 1,4 polymer of glucose. So that's about 20% of the starch by weight. And then about 80% is called amylopectin. And this includes a bond that we haven't talked about. Oops, sorry, I forgot my A. Oops, amylopectin. I didn't mean to dot YY, I just wasn't thinking. Amylopectin actually includes a 1,6 prime glycosidic bond. So it's a 1. So we'll go like drawing my little ring like this, right? And then I'm connecting to a 4. So this is the majority of the amylopectin, but it turns out on carbon number 6, so here, I start another branch. So this is, remember, this is the number 6 carbon, so you could call that 6 prime, and this is 1. So this is an alpha, it's an alpha 1,6 prime glycosidic bond. And so it has these branches built into it. So I have the linear chain like I have in amylose, but about every, and this is where it gets a little dicey because people will say different things, I think depending on what they're studying, honestly. But the original numbers I heard when I was learning this stuff is this branching occurs like approximately every 25 residues. So what this effectively does is increases the number of ends from which the enzymes which process amylose and amylopectin, it increases the density of ends in the molecule so that the energy can be gotten out a little bit faster. So when you're looking at an amylopectin molecule, then you're starting with residues that look like this. And then what you have is a branch to another branch. Let me do a little circle because that's easier. So this one on the top is the 1,6. This is the 1,4, and then it does this again. And then this one will at 25 residues or so. And I've heard numbers as low as 11. So 11 would be high density of ends, and then high densities of sugars, and also an ends of the sugar, as well as more branching is what that would mean. So you have these branches like this, and like I said, about every 25 residues on every linear chain, there's a branch. And so you can imagine what this might look like if you were to start at the bottom and work your way up. It would branch out like this, and every single one of these branches could have a branch growing or two growing off of it. And so what it ends up looking like actually is like a tree. So I'm drawing these, and then these have branches, and then these have branches, and there might be a branch here. And so anyways, it kind of looks like a tree, and that's the way that I think about it. Now, the thing is, in people, so this is starch, and it's amylose and amylopectin. In humans, in animals, we actually have something called glycogen. And glycogen, rather than the amylopectin, really the difference of glycogen to amylopectin is that glycogen branches at a much higher frequency. So if this is the tree for amylose, amylopectin, right? This is the tree. Then the glycogen tree would just be much more dense. So it would start here, it would start branching from the bottom a little faster, and each one of these would branch, and then you can just imagine, so it's going to be this whole hairy kind of mess. And I often refer to this as a survival tactic for animals versus plants, because the ends of the sugar molecules, the ends of the polysaccharides, are where the glucose comes off of to give you energy, and then the more ends you have, the more quickly you can access that energy. And as I explained to people, like in a plant like a potato, you have amylose and amylopectin. It's not like a potato goes running away from a predator. It just sort of sits there and gets eaten. On the other hand, if a predator came to eat you, you would need to use your energy and take off right away. So that's kind of the idea of the difference between amylose and amylopectin and glycogen. And in animals, like I said, we have a high degree of branching, and that's what we call glycogen. The last thing to talk about really is the sugars that are found in DNA and RNA. And I apologize, this should say DNA and RNA. And we're going to start with RNA. The R stands for ribose. And if you remember, ribose has this structure. And if you don't remember, you can always just go look at it, right? So, and then a CHO at the top. So it's an aldopentose. But the aldopentose also makes a furanose. And in the furanose, we have a 5-membered ring. And so we would draw the closed ring structure looking like this. And then on the, this could be up or down. Remember, that's the anomeric carbon. But then these guys have to all be going in the same direction. So this is 1, 2, 3, 4, and this is 5 on the ring. So we're going 1, 2, 3, 4, and 5. And so this is a D sugar. So this group goes CH2 and then OH like this. So that's the CH2OH. That's actually down here. So let me highlight a couple of those things just so you see those a little better. That's the CH2OH there. And then oxygen, this oxygen is actually that oxygen in the ring to make the 5-membered ring. That's not the nomenclature numbering, that's just to get the ring size, right? So when you have RNA, you have ribonucleic acids, and in a ribonucleic acid, what you have is you have a substitution at this position. How do I want to do this? At this position, and you have what's called a base, and the base is, if you remember, we had like guanine, cytosine. We talked, or actually, did we talk about those in this class? I talked about them in a class recently. I thought it was this class, but it might have been my other organic chemistry class. But you have a base that substitutes that at that position, and then you have a phosphate link between this carbon and the adjacent sugar, and that linkage, I'll just draw it off screen real quick, and then I'll talk about it a little bit. Sorry, my headphones keep turning off, so that's why I'm sometimes suddenly in blank for a while. Here's the basic structure for 2 ribonucleic acids connected together. Now they'll have bases on them, that's what this is. And those bases are those like guanine and the cytosine and things like that, those kinds of bases. And then, or is it uracil? It might be uracil in RNA actually, but that being besides the point, to talk about the basic structure here, the way we describe this is there's a sugar here, residue, and a base that's attached, and then it's a phosphodiester linkage. Now remember, an ester is like a carbonyl and then an R group. So in a with phosphate, you can have a carbon group on 2 oxygens, and so it becomes what's called a phosphodiester bridge. And then I have numbering, and I already showed some of the numbering. So 1, 2, 3, 4, and then this is 5 for the ring, but I'll leave that off. Actually, that's actually wrong. That's 5 for the carbon, and then the oxygen like this. 5, and then oxygen and another phosphate. So this is where another residue for the nucleic acid would be. That's a P right there. Okay, so this is ribonucleic acid, and we would number this with these to the right, just like we showed before. These are the primes. So this is in the 3 to 5 prime direction for the bond, is what they'll say. So a 5 to 3 prime. I got that backwards. Oh, no, they say 5 prime to 3 prime. That's what it is. Yeah, they say 5 prime to 3 prime because these are all connected up to each other on different sides. So they'll say 5 prime to 3 prime is what they'll say. 5 prime to 3 prime. Okay, so now then there's DNA, and DNA is deoxyribonucleic acid. And the way that it's a deoxyribo is because if you're looking at the ribose that makes up DNA, there's no OH group here. So where it differs is it differs at this point here from this point here. So that's, besides one of the bases being different, is that at carbon number 2, the oxygen is missing in DNA. So that just sort of summarizes our chapter on carbohydrates. If you have any questions, feel free to send me a message.